Hello and welcome back. Alright, so last class slash lecture slash video slash whatever you want to call it. We kind of went through the basics of hypothesis testing. And we looked at this idea of like a null hypothesis and an alternative hypothesis and a p-value and a threshold value and all these other fun terms. But we didn't actually kind of go through the mechanics of carrying one out. So that's what today is going to be, like the actual physical mechanics, the process, the math behind carrying one of these out. Now, if we were in class, we'd start with like an activity where we gathered some data and then use that data to do one. We're going to kind of have to just fudge it today. All right. But all the same, let's see what we've got here. So most people believe that the proportion of heads is 0.5 when a coin is flipped. But what about the proportion of heads when a coin is spun? So give the null an alternative hypothesis for the penny experiment. All right. So given that a coin is 0.5 when a coin is flipped, and the null hypothesis is usually the hypothesis of no difference, we will start with a null of saying h sub 0 is that p equals 0.5. Right. Now, our alternative, and we don't really know, like spinning a coin, does that make heads more likely? Does that make heads less likely? We don't really have a starting hypothesis. So given that, our alternative isn't going to be that p is less than 0.5 or p is greater than 0.5. We're just going to say that our alternative hypothesis is that p is not equal to 0.5. It's something different from 0.5. And again, because we're ethical researchers, we're going to pick our alpha ahead of time. We're not going to pick it later to fit what we want. So we're going to set our alpha level at 0.05, which is what we're going to use 98% of the time in here. All right. So again, this is our alpha level or our threshold value, or this is the point at which we will actually reject our null and accept our alternative. Okay. So because we did not equal to 0.5, that means we're doing a two-tailed test. And if this is sort of the distribution of what could be expected if this were true, we're going to conduct our experiment, and if we get an experiment that ends up down in this part of the curve or up in this part of the curve, we're going to say, hey, that was pretty unlikely, and we're not really sure that the null is true. If we get an experiment that ends up in this white part of the curve, then we're going to say, all right, there wasn't enough evidence to reject this claim. So these are our rejection zones, and it's basically 2.5% of the curve on the left side, and it's 2.5% of the curve on the right side, which is where that threshold value of 5% is coming in. All right, so again, these are going to be our rejection zones, and this area in here is our fail to reject zone. All right, so we need some data. All right, this is where I would pass out coins. Everybody would start spinning their coins. Some people wouldn't actually be able to spin their coin, and it would be embarrassing for them. But let's just fast forward through all that, and we'll pretend that we got 56 heads out of 135 spins. All right, which would work out to be 0.4148. Okay, so the question that we're now going to need to ask is, what were the odds of getting a sample result like this, assuming this is true? And if the odds are really high, then we're going to say, all right, we don't have enough evidence to say that this is true, that this is wrong. But if the chances were really low of getting this, then we'll say, hey, our starting theory was probably wrong because there was a really small chance of getting this result. All right, and that's kind of the general idea here. All right, so if we look at the notes here, it says, well, our number probably isn't exactly 0.5. Yeah, it's not, because it's an experiment and there's always going to be some random variation. But how likely is it to get a proportion as extreme as this simply due to sampling variability if 0.5 is the true proportion? All right, so same as confidence intervals, we have some conditions that we want to make sure are in place. We want to make sure that it's randomized. All right. So when you're like selecting people or when you're creating your sample, it should be random. Here we're just flipping, like spinning coins. It's a pretty random process, so we're fine there. Now, again, it's this whole idea of when you're sampling without replacement, it's important that your sample is no less than, your sample is no more than 10% of the population. But here we have true independence. One coin spin is totally independent from another. So the idea of like sampling with or without replacement doesn't really apply here. But I'm just going to put like independence, which is what we have in this case. Each coin spin is truly independent from the other one, or the 10% condition where your sample has to be less than 10% of the population. And that's where, again, we're sampling without replacement. So things are not truly independent. And then the last one, to be able to use the normal approximations that we want to use, you have to have the 10 success and the 10 failure condition. So these should all be pretty familiar at this point. They've been popping up for the last 2 or 3 units. And it's just the sort of stuff that we need to have in place when we're doing any sort of confidence interval, hypothesis test, etc., etc. All right. So those are all in place for our little imaginary experiment here that didn't actually happen. So let's look at the process of carrying out a hypothesis test. All right. So compute the sample statistic and the standard deviation of the statistics. So the sample statistic is just the data that we gathered. All right. So that was our 56 out of 135, which we already said was 0.4148. All right, the next thing is the standard deviation of the statistic. So when we do the standard deviation of the statistic, we're going to be using our formula that we've been using. So that is the square root of PQ over N. And the P and the Q that we're going to use the P from our null hypothesis. Because again, remember, we're working on the assumption that this is true. All right, so we're going to use the P from our null hypothesis because we're working on the assumption that that's true. All of our study, all of our analysis is based on this idea that this is true. And we want to say, what are the odds of this happening, assuming this were true? So if we assume this is true, we're not going to use the 0.4148. That's just our sample result. We're going to use the 0.5 from our null hypothesis. Because again, everything is based on the assumption that that null is true. So this is going to be 0.5 times 0.5. All right. P was 0.5, which means Q also has to be 0.5 over 135. Because what we really want to know is we want to know what's the standard deviation when the proportion is truly 0.5 and your sample size is 135. Because everything is based on this assumption that this is true. And this is going to work out to be, let's see here, right. It's kind of hard to see this, but all right. 0.5 times 0.5 divided by 135, and then we'll take the square root of that, and we get 0.043. All right, so 0.043. All right. Next, compute how many standard deviations away your observed score is from the sample proportion of the null hypothesis. All right, so let's put that in terms that are a little easier to understand. So it's saying compute how many standard deviations away your observed score is from the sample proportion of the null hypothesis. So p hat would be our sample proportion. P would be our null hypothesis. And then we're trying to see how far away are these two things in terms of standard deviations. So that's the standard deviation that we just calculated. So we want to know how far away are those in terms of standard deviations. So p hat, again, is our sample statistic. Let me make that a little clearer up here. This is p hat. All right, so p hat would be 0.4148. All right, the p from our null, all right, this is coming from our null, is just the 0.5. All right, let me make that a little clearer. This is coming from our null. This is coming from our data. All right, and then the standard deviation we calculated up above, that was the 0.043. And again, that's the standard deviation of our statistic. All right, so this should look pretty similar because it's basically our z-score formula. All right, the z-score formula was the observation minus the mean divided by the standard deviation. All right, there's basically our observation. Not exactly a mean, but you get the idea. There's our standard deviation. All right, and you can kind of think of this as a mean because it is the mean of the sampling distribution, but either way. All right, so if we do this out, we're going to end up with negative 1.98, which is saying that our data that we gathered was almost 2 standard deviations below the mean. All right, remember that negative 1.98 is in terms of standard deviations. So this is basically saying we were 2 standard deviations below the mean. All right. So next, we're going to find our p-value, which is basically the portion shaded on the normal model. All right. So anytime we need to find the portion shaded on the normal model, or the percent shaded on a normal model, that's an NCDF. So we can do an NCDF. And we want to know what are the odds of being 2 standard deviations below the mean or more. All right, we always want to go like or more extreme. All right, so we're already 2 below. What are the odds of being even more than 2 below? Now, because this is effectively a z-score, we actually don't need to specify the mean and standard deviation. It'll be the defaults, which are just 0 and 1. All right, those are the defaults usually in the calculator, but if you've been switching them, you might have another number in there. But just anytime we're using a z-score, remember we are using the defaults, which are 0 and 1. All right, so I could go here into my calculator. I could bring up NCDF. I could say I want to go from negative 9999 to negative 1.98. I've got a mean of 0, a standard deviation of 1, which again are the defaults. And when I hit enter, I'm going to get 0.0238. Let's see, what is it? 0.02385. So we can say 0.0239, we'll say. 0.0239. Now, if we look at this little bubble here, it says if it is one-tailed, test normal CDF works just fine. If it's a two-tailed test, find one tail and multiply by 2. And here's kind of what's going on here. All right, when you do the two-tailed test, all right, you've got 2.5% on this side and 2.5% on this side. Now, we said that our threshold value was 5%. All right. So what we do is, with a two-tailed test, technically it's not 5%, it's 2.5% on the left, 2.5% on the right, versus a one-tailed test where it's 5% all on one side. So what we do to kind of make it uniform is, instead of saying that, like, when you're doing a two-tailed test that your p-value actually has to be under 2.5%, what we do is we take this p-value and we just double it. That way we can still use the 5% threshold. So I'm going to take this 0.0239, I'm going to multiply it by 2. I'm going to get, again, depending on how you sort of round things here, technically when I do this one, I'm going to write it as 0.0477 because I kept it all in the calculator and that's a more accurate representation. It's not exactly what you would get if you multiplied this by 2, but if you take the full answer, it is what you get. So I'm going to just keep it like that. Because this allows us to still use that same 5% threshold. Instead of having to say, oh, this was a two-tailed test, so my threshold is actually 2.5% instead of 5%, we just double what we get from this for two-tailed tests and say, oh, you know, that is either under 5% or it is over 5%, and then go from there. All right. So, long story short, we do this NCDF. If it's a two-tailed test, multiply it by 2. If it's not a two-tailed test, you can just leave it be and you don't have to do anything. All right, so interpret your p-value in context. What this is saying is that we have a 0.0477, or we could write, or 4.77% chance of getting a sample result of p hat equals 0.4148 if there were truly a 50-50 chance of getting heads or tails when spinning a coin. All right, so that's a pretty small chance. All right, so we're now left with two options. We either ended up with a really unlucky sample that only had a 4.77% chance of happening. It is possible that that's what occurred. Or what's more likely is that our initial assumption was wrong. There is in fact not a 50-50 chance of getting heads or tails when you spin a coin. And that's actually true because when you spin a coin, there's more weight on one side of the coin than the other, and that causes it to fall to one side more often than other. So anyways, our conclusion would be, because 4.77% is less than our alpha 0.05, we reject the null and accept the alternative hypothesis. So that's kind of the full procedure for walking through a hypothesis test. All right, so let's get a definition down for our test statistic. Then we're going to just run through a quick couple of bullets, and then we'll do some practice. All right, so test statistic is a measure of how far an individual sample diverges from what we would expect if the null were true. And then let's add the test statistic is measured in standardized units. Which means we're adjusting for how spread out things are, which means basically we're dividing by the standard deviation. So the test statistic, which we already calculated up above, equals the statistic, which we get from the data that we actually gather, minus the parameter, which we're taking from the null hypothesis, divided by the standard deviation of the statistic, which again, even though it says standard deviation of the statistic, we are using the value from our parameter to actually calculate that formula. All right, and this is what we did up here in step 4. All right, when we commuted how many standard deviations away the score was. All right, so that's kind of what we were doing when we did that problem there. All right, so a couple of bullets, and then we'll stop this video and start a new one with actual practice problems. So, couple of reminders here. The parameter is the value for the proportion from the null hypothesis. So anytime you see parameter, you're getting that from the null hypothesis. The statistic is the value from the individual sample that is used to test the hypothesis. We're getting that from our data. And then the standard deviation of the statistic is calculated using the appropriate formula. Use the p from your null hypothesis, not the calculated proportion. And again, there's the formula. All right, so all those pieces are going to be important when we're kind of going through these things. So let's actually try some of these problems just so that we can get the hang of them and see how they work. All right, a report on healthcare in the U.S. said that 28% of Americans have experienced times when they haven't been able to afford medical care. A news organization randomly sampled 801 black Americans, of whom 38% said there had been times in the last year when they have not been able to afford medical care. Does this indicate that the problem is more severe among black Americans? Test an appropriate hypothesis and state your conclusion. Make sure to check any necessary conditions and to state a conclusion in the context of the problem. All right, so first things first, necessary conditions. It says it's a random sample, so that's good. 801 is definitely less than 10% of the population. And 38% of 801 is definitely going to give us 10 successes and 10 failures. So we're fine there. All right, so let's start with our null hypothesis. So our null hypothesis is the statement of no difference. So we're going to assume that, in fact, black Americans are no different in their experience with the healthcare system. So that would be that P equals 0.28. Okay. The alternative so H sub A, we have to read the problem to get what the alternative is going to be. And this one says, does this indicate the problem is more severe? So we're not just saying, is their experience different? We're specifically saying, is it more severe? So we're going to write that as P is greater than 0.28. And then our alpha, we're just going to keep at 0.05, which again, unless the problem tells you to use something different, just always assume that in this class we're going to be using 0.05. All right, so our next step is to generate our test statistic. All right, so our test statistic, if you remember from just last page, is the statistic, which is coming from the sample, minus the parameter, which is coming from our null, divided by the standard deviation of the statistic. And again, we use the parameter values to calculate that. All right. So if we look here, our statistic, the problem tells us, was 0.38. That's what we got from our sample. The parameter that we're using from our null hypothesis is 0.28. All right. And then the standard deviation of our statistic is the square root of PQ over N. All right, we've been using that for a while now. All right, I'll put that off to the side here, PQ over N. And again, we're using the P from our null hypothesis. So that's going to be 0.28 times 0.72, because P and Q always add up to 1. And then we're going to divide by N, which the problem tells us is 801. All right. So if we were to go through this, we would see that the top of this is pretty easy to see. It's just going to be 0.10. All right, the bottom is a little harder to see, but that's going to be like well, let me just do it on the calculator here. All right, 0.28 times 0.72 divided by 801, and then take the square root of that. We've got 10586, so we'll just say 0.0159. 0.0159. All right. And then when we actually do this, you're going to get something like roughly 6.30. Again, there's some rounding going on here, but roughly 6.30. So that's our test statistic. Now, we want to find out what were the odds of being basically 6.3 standard deviations above the mean. All right, so intuitively, you should expect this number to be pretty small, because 6 standard deviations above the mean is quite a few standard deviations. So we'll do an NCDF from 6.3 to positive 999. Now, notice on the first problem, we went from our answer to negative 999. This one, we're going from our answer to positive 9999. And basically, the way that it works is if your test statistic is positive, you're going to go from that number to positive 9999. If your test statistic is negative, most of the time you're going to be going from that number to negative 9999. So again, if it's positive, you go to the positive direction. If it's negative, you're going to the negative direction. Most of the time. All right, again, the mean is 0, the standard deviation is 1. All right, and if we put that in our calculator, distribution, NCDF, 6.3 to positive 9999, when this mean is 0 and the standard deviation is 1, what you're going to get is a very, very tiny number. All right, notice the E on the right-hand side there. So that's 1.49 times 10 to the negative 10th. Or another way of writing that would be our p-value is a decimal point, 9 zeros, 3, 4, 5, 6, 7, 8, 9, and then a 1, 4, 9 after that. All right, so a very, very tiny number, which says there's a really, really small chance of getting this result if this is the true value. So now that we see that our p-value is so tiny, we can write a conclusion that says because our p-value is under 5%, which was our threshold value, we reject the null and accept the alternative. All right, we're basically saying there's no way this is the right value for Black Americans, because if it was, we only had this % chance of getting the sample result. So chances are that the true value is actually higher than 0.28. All right, what's your test? One-tailed upper, one-tailed lower, or two-tailed? Explain why you chose this kind of test. All right, ours was one-tailed upper because we were checking for higher rates. All right. And then explain what your p-value means in context. All right, so basically there was a 1.49 times 10 to the negative 10. I don't want to write out all the zeros again. All right, chance of getting a sample result of 38% if the true value for the population is 28%. Which basically means we either got the world's unluckiest sample, or in fact, it wasn't actually 38%. It was 28%. It was something higher than that. All right. So again, that's sort of the process that we're going through when we do these problems. So let's take a look at a couple more, just because again, we got to get used to these, and there's a lot going on here. All right. Ingots are huge pieces of metal, often weighing more than 20,000 pounds, made in a giant mold. If they crack while being made, their integrity is compromised. Even though the metal can be recycled, the cost for this is more than $10,000. All right, not good. In one plant, that should say in one plant, not in on plant, only 80% of the ingots have been crack free. To reduce the cracking proportion, engineers made some changes in the casting process. Since the changes were made, 400 ingots have been cast, and only 17% of them have cracks. Should management declare victory? Has the cracking rate really decreased, or was the 17 just due to bad luck? All right, now first things first, in one plant, and if 80% of the ingots have been crack free, that's another way of saying 20% have cracks. All right, so should management declare victory? Has the cracking rate really decreased? So again, the process that we're going to start with is we start by making sure our conditions have been met. Now, we don't know how many of these things this plant produces, but we're going to have to assume that our 400 is less than 10% of the population, because we don't really have a choice here. We're going to hope that they were randomly selected, and then we also can recognize that with 400, we are at least sure that we'll have the 10 success and 10 failure piece. So that's good. All right, so we'll start with our null hypothesis. And that's always the statement of no difference. So we're going to say that P is still 0.2. All right, we're going to write an alternative, which is that we've actually improved the process. So now P is less than 0.2. And again, you kind of just have to get that by reading the problem and interpreting it. You know, this says, has the cracking rate really decreased? So we're looking at a less than situation here. Our alpha, we're going to keep at 0.05. So the next thing that we're going to do is calculate our test statistic. All right, and again, that equals our stat minus our parameter divided by the standard deviation of our stat. All right, so in this case, our stat is 0.17. Our parameter is 0.2, coming from the null hypothesis. And when we calculate the standard deviation of our statistic, we're using the 0.2, not the 0.17. So this is going to be 0.2 times 0.8 over 400. All right. And then let's see what we get here. All right, so I'm going to do the standard deviation first. 0.2 times 0.8 divided by 400. Take the square root of that is negative, or sorry, 0.02. So 0.17 minus 0.2 divided by 0.02 gives us negative 1.5. All right, so this all works out to be negative 1.5. Then we're going to use a normal CDF. And again, because this is a negative situation, we're going for less than, it's going to be negative 999 to negative 1.5. Again, you can put in the 0 and the 1 there, but those are the defaults. So if you don't write 0 and 1, that's what's assumed. All right. This is going to give you 0.066807, which you could also think of as 6.68%. All right. So based on this, our conclusion is going to be a little different this time. We would say, because the p-value is over 5%, we fail to reject the null. And just remember, going back to yesterday, or last video, we never accept the null, we just fail to reject it. There wasn't enough evidence based on our sample to say definitively that they have improved the process. All right, 17% getting this as a sample result had a 6% chance of happening. And you might be saying to yourself, well, 6% is still pretty low. I don't disagree, but the threshold that we set was 5%. So because it's over 5%, we're saying, you know, sorry, it doesn't cut it. You know, basically what happened is, here's our curve, here's our rejection zone. We got something, you know, right here, just outside of the rejection zone. So it was close, but it wasn't close enough that we're actually going to reject it. All right. Male babies. Advances in medical care, such as prenatal ultrasound examination, make it possible to determine a child's sex earlier in a pregnancy. There's fears that in some cultures, this technology may be used to select the sex of their children. A study from Punjab, India reports that in 1993 in one hospital, 56.9% of the 550 births that year were boys. It's a medical fact that male babies are slightly more common than female babies. The study's author reports a baseline for the region of 51.7% male births. is there evidence that the proportion of male births has changed? Okay, so again, walking through our process here, it's one of the things you always should check for the conditions. So is it randomized? Is the sample under 10% of the population? Do you have 10 successes and 10 failures? I mean, in a classroom setting, yeah, those things are in place because otherwise you can't do the problem. But those are things that you always want to be considering. So we can skip ahead to our null hypothesis. So we're going to say P equals 0.517. It's the statement of no difference, and I'm getting that because it said it was the baseline for the region. So we're saying that, it's still the same. Nothing has changed. All right. Our alternative is we're kind of worried that people are trying to have more boys. So our alternative is going to be that P is greater than 0.517. And then our alpha is going to stay at the 0.05. Again, so we start with our test statistic. So our test stat, which again is the statistic, which for us was 0.569, minus the parameter, which is that baseline number they gave us, 0.517, divided by the standard deviation of the statistic, which again for us, we're going to use the parameter values of 0.517, which means the other one is going to be 483, because those always have to add up to 1. And it told us in the problem that our sample size was 550. So 550. All right, and I'm just going to kind of skip ahead to the calculations here and let you know that that is 2.44. Okay, so it's 2.44 standard deviations above the mean. So we're going to take this, we're going to use it in our NCDF. We're going to say 2.44 to positive 9999, because again, this is like a greater than situation. And then our mean is 0, our standard deviation of 1. Again, if you don't write those, it's assumed. And when you put this into the calculator, you are going to get something like 0.007. Or another way of thinking of that is 0.7%. All right. So there's a pretty low chance of that happening. Now, again, remember, if this was the curve based on this assumption, we'd have our rejection region over here, which is the top 5%, and we're like way over here, all right, in that 0.7% range. So that means we're in the rejection zone. So our conclusion is going to be, because our p-value is under 5%, we reject the null and accept the alternative. So it does seem like something's going on here where they're ending up with more male births than otherwise would be expected. Okay? All right, one last page, and then we will call it quits. All right, so confidence intervals versus two-sided tests. A 95% confidence interval gives you an approximate range of P's that would not be rejected by a two-sided test at the 5% significance level. So we're going to see there's kind of this overlap here where the confidence interval gives you all of these possible values for the true proportion, which is sort of the same side of the coin as the hypothesis test. If your number falls in that range, that's a fail to reject situation. And if it falls outside of that range, it's a reject situation. So if we look at these other bullets here, when the sample proportion falls in the reject zone of the normal distribution, the confidence interval will not contain the null hypothesis. when the sample proportion falls in the fail to reject zone of the normal distribution, the confidence interval will contain the null hypothesis. Now, the link isn't 100% perfect because the standard error used for confidence intervals is based on the sample proportion, which means it's using p hat and q hat over n, whereas the test statistic is based on p sub 0 from the null hypothesis, which means it's not using p hat and q hat, it's using p and q. So it's not 100% the same, but it's very, very close. So what I'm going to show you here is a couple of things. One, I'm going to show you that they reach the same conclusion. And then two, I'm also going to show you how to do hypothesis testing on the calculator. So according to the CDC, 50% of high school students have never smoked a cigarette. Martin wonders whether the national result holds true in his small rural high school. For his class project, Martin surveys an SRS of 150 students from his school. He gets responses from all 150 students, and 90 say that they have never smoked a cigarette. What should Martin conclude? Create a confidence interval and conduct a hypothesis test to support your answer. All right, so if we're going to conduct our hypothesis test, we're saying h sub 0, p equals 0.5, because that's the CDC's number. And then our alternative is going to be that p does not equal 0.5. Because again, this connection with confidence intervals and hypothesis testing only works for two-sided tests. Our alpha is still going to be 0.05. So what we can do on the calculator is if we go to stat tests, you're going to see a one prop z-test. It's going to ask you for p sub 0, so that's our starting null, or 0.5. It's going to ask you for the number of successes, which in this problem they told us was 90. And it's going to ask us for the sample size, which the problem told us was 150. It's going to ask whether you're doing not equal to, less than, or greater than. We're doing not equal to, and then we can click calculate, and it will give you your test statistic. So our test statistic was 2.45. It'll give you the p-value. All right, so the p-value is that second one there, which was 0.014. And then the other things listed there are just what the sample proportion was. So the sample proportion was 0.6 and the sample size. So it's really the first two that you care about. So based on a p-value of 0.014, we would reject the null. Now let's do our confidence interval. So over here, if we set up the confidence interval, all right, I can go back to stats, I can go back to tests, I can go to one prop z interval. All right, the numbers are already in there for me, 90, 150. I'm going to change the confidence level to 95, and I get an interval of 0.5216 to 0.6784. All right, and what you'll notice is this interval does not contain the null of 0.5, which is exactly what we would have expected. All right, this was saying that we were rejecting the null. We're saying 0.5 is not the true value, and when we created the interval, 0.5 was not inside of our interval. All right, if we had failed to reject the null here, you would have seen this interval would have contained 0.5. But since we rejected the null and said this is not an option, our interval should not include that as an option, and it doesn't. All right, it starts above 0.5 and then it only goes up from there. So what we're going to see is that these two things are really kind of two sides of the same coin, but it only works when you're doing the two-tailed test. All right, when you're doing a one-tailed test, there is no connection. It only works for the two-tailed tests where you're looking at kind of both sides, and then you have your interval there in the middle. All right, so that wraps this up. I hope this was helpful. I'll put some practice problems up, and we'll see how they go. All right, bye.